And within this setup, we consider upright paths, directed paths. So they can only move up and right at each step. They cannot move down or left. And we consider, for any such path, we associate to it the weight of the path, the weight being the sum of the random variables which it passes through. So these paths, though I've drawn them as edges, they're actually the vertices that they pass through. And you sum up the random the values associated with the vertices, you get the weight of the path. So obviously there are a lot of paths from 1, 1 to r, which are upright in this way. And we can maximize the weight of any given path over all such directed paths. And we call this weight XR. So in the entire talk, XR is going to be the weight of the maximum weight from between these 2 points. And of course, this is also attained by some particular path. And the path, we will call such paths geodesics, the ones which attain the maximum weight between the 2 given endpoints. So having defined this random number, a natural question is, how does it grow as a function of R? And to first order, XR is linear in R. There is some almost sure deterministic constant, mu, such that XR over R, the limit of that is mu. So if you make no assumptions on the vertex weights, mu can be infinite. But as soon as you make some mild moment assumptions on the vertices, then mu will be finite. So the reason you have this limit is because XRs have this nice superadditivity property, which means that, so if you look over here, so you have XR plus S, and that will be at least XR plus X tilde S, where X tilde is an independent copy of XS. So just as a depiction, so if this green path is the one which attains the maximum weight, you can also consider this alternate path, which passes through the point R, R. So this blue path is from 1, 1 to R, R, and the red path is from R, R to R plus S, R plus S. So the concatenation of these 2 paths is also a path from 1, 1 to R plus S, and therefore it's a candidate which is being maximized over for XR plus S. So you get this basic inequality just by considering the fact that this is just one among the many possible paths. So this is very important. This inequality will be something which we rely on quite heavily throughout the talk. And also note that this mu statement, the existence of this constant mu, makes no claim about the vertex weights. This is always true modulo the moment condition which I mentioned. Also, if you have any questions, please feel free to stop me and ask anytime. Yeah. Okay, so this is the leading order term. Of course, after the leading order term, we also have fluctuations around the leading order term. And it is believed that the fluctuations at XR will be non-Gaussian and of order R to the 1/3. So if it was Gaussian, it would be R to the half. But because you're doing this maximization over all possible paths, you reduce the fluctuation. And it's a lower order term of 1/3. So this is not known for most vertex weights. This is really known only for exponential weights and geometric weights in the planar case or in the lattice case. But this is expected to be true in greater generality, of course. So when you center and scale, so when you center XR by this leading order term, and then you scale it by the fluctuation order, up to a constant, you should be getting the GUE Tracy-Widom distribution. And this is known, again, in the case of, in the integrable case, when you have exponential random weights. This was proved by Johansson in 2000. So the Tracy-Widom distribution is also non-Gaussian. So in particular, the Gaussian distribution has certain tail exponents of 2 for both upper and lower tails. The Tracy-Widom distribution has different exponents. It has 3/2 for the upper tail and 3 for the lower tail. And of course, it's should be noted that these are different. It's different for the upper and lower tails. We'll be talking more about why this is and how to get these exponents later in the talk. So this theorem I've just cited from Ramanas, Ryder, and Verlag in 2011, though I suppose it was known earlier as well, but this is a slightly more, it's a clean statement that I just cited. Okay, so we said 2 things. We said that exponential LPP converges to Tracy-Widom, and the Tracy-Widom has these kind of tail exponents. So a natural question is whether you have these tail exponents at the finite R case before you take a limit for LPP models. So again, this is known in the integrable case of exponential LPP, and I think also geometric LPP. And this result I've written over here is kind of collecting together several different things. So let me just quickly summarize that. So Johansson's paper, which I've already mentioned, proves that XR has the same distribution as the top eigenvalue of the Laguerre unitary ensemble. Which I won't define, but it has that's what the top eigenvalue agrees with for XR. And the second paper, Ledoux and Ryder and Doe and 10 show these two upper bounds for the top eigenvalue of the LUE. They say that their methods should give you this missing lower bound over here, but they don't prove it, so I haven't mentioned it over here. And this lower bound on the lower tail they say would not be obtainable by their methods, and that was proved last year by Riddhi Basu, Shirshendu Ganguly, myself, and Manjunath Krishnapur. And one thing to note here is that these inequalities only hold up till r to the 2/3. They don't hold all the way for the entire tail. It's only up to a certain number, which we'll be coming back to in some time. So our main result is going to obtain such inequalities under some natural assumptions, which we'll describe soon. But before we get to that, I want to talk about the use of some similar assumptions in a non-integrable model of first passage percolation.
So for the tail behavior, do you expect similar behavior beyond r to the power 2/3?
No. So for example, let's look at the lower tail, for example. XRs are necessarily positive, non-negative. So when t becomes, for example, 4r to the 2/3, this second term becomes 4r, right? So this whole probability will become 0 at that point. Mm-hmm. So this lower tail would not even hold beyond that for one thing. Mm-hmm. For the upper tail, similar things happen when you enter this r to the 2/3 regime. Basically, the individual vertex random variables play a much bigger role, and this would become replaced by something like tr to the 1/3. So basically, this term would just appear over here in the exponent. Okay. The basic principle is that once you get really big, the individual vertex weights start influencing the overall behavior. Mm-hmm. But yeah, up until some range, you do expect these exponents.
Okay, thanks.
Yeah. Yeah. So first passage percolation is similar to LPP in that you consider paths on the lattice, but instead of maximizing the weights, you minimize them, and you also don't impose any oriented conditions. So you don't consider only upright paths; they can also go down or left, so long as they minimize the weight between the given points. So progress in FPP has been much harder than LPP because of a lack of these connections to representation theory and similar formulas. And whatever progress, well, not whatever, but much of the progress in the last maybe 2 decades has been after taking certain assumptions and then seeing what are the consequences of those assumptions. So I'm just kind of mentioning 2 examples here. So in 2013, Saurav Chatterjee showed that under certain assumptions on the fluctuations of the analog of XR, that you can prove something called the KPZ scaling relation, which I won't define here. But the point is that it's the analog of us saying that XR fluctuates on scale r to the 1/3, basically. And then Offinger and Damron expanded Chatterjee's assumption set. Sorry, as in they expanded the class of vertex distributions to which Chatterjee's result applies to, and made the proof a bit simpler. And the second example that I want to mention is that is Newman and Kiza from 1995, who show that under certain assumptions on the curvature of the limit shape, you can get results about the fluctuations of the weight minimizing path, about how it fluctuates. So I have not defined what the curvature or what the limit shape is in LPP, but I'll be doing that next, because that's also going to be one of our assumptions in this paper. Okay, so we saw that if your path is ending at r comma r, the leading order term is mu r. But you could end elsewhere on this line. You don't have to end only at this midpoint r comma r. So suppose you end at, say, r minus z, r plus z as a function of z, then the point is that you will be suffering a loss in your weight, actually. And it'll be the amount of loss you suffer is parabolic in the distance you go outwards. So in fact, it'll be mu r minus some constant z squared over r. So this is known again in the integrable cases of exponential and geometric LPP, and is expected to be true in greater generality. So just as a depiction, so this might be your best path ending at this point, and this would be its mean. The point on the parabola would be the mean weight of that path. And as you go along, it changes depending on where you end on the parabola. So one thing to mention is that this thing I've drawn over here, this parabola, it has some noise to it. So in fact, it's not the limit shape itself; it's the expected weight at finite r. So there's no limit being taken, and because of that, you have this fluctuation term of scale r to the 1/3 for both these expressions. And we'll be using something similar in our assumptions. Okay, so with that, we can move on to describing another important feature of the geodesic paths, which is how much they fluctuate. So we've already talked about r to the 1/3 being the fluctuation of the weight itself. But as we said, the weight is attained by some particular path, the geodesic. So you can ask, how does it fluctuate in a geometric sense around its interpolating line between 1, 1 and r comma r? And it turns out that this is of order r to the 2/3. And the reason is relatively easy to see if you accept the parabolic loss in weight as you go out. In that the loss in weight you suffer when you are out by order r to the 2/3 is exactly the same as the r to the 1/3 weight fluctuation. So r to the 2/3 squared over r, so that's z squared over r, is exactly of order r to the 1/3. So because these two exponents match at this value, this is what you should expect to see as the fluctuation level. So this will appear kind of implicitly at several points in our arguments, though not in the assumptions itself. Okay, so that's all right. So we can go on to stating the assumptions and then the main results. So the first assumption is quite trivial. So as I said, if you don't make any assumption on the vertex weights, the leading mu can in fact be infinite. But under a mild moment assumption, so for example, that the vertex weights have finite third moment, this would be finite. So we're just assuming that it is finite to avoid any pathologies. The second one is involving the limit shape, which we just talked about. So xzr over here is the weight from 1, 1 to r minus z, r plus c. So this is the thing that suffers the gz squared over r loss in weight. And then we also encode the order of the fluctuations, which we expect to be of r to the 1/3. So we don't assume this everywhere. We only assume it in a neighborhood around r comma r, but it is very important. The second assumption encodes this fluctuation in a slightly stronger sense. Well, not a stronger, but in a different sense. So it says that the probability that you fluctuate away from this expected value decays in a stretched exponential manner. So there is some small positive alpha such that the probability of going above by t on the correct scale is at most e to the minus t power alpha. So much of the theorem is going to be in taking this initial alpha, which could be arbitrarily small, and bootstrapping it up till you get the right or the optimal exponent of 3/2. And we assume this uniform direction in that in most directions, not all, but in most directions, you have this kind of bound. And the final assumption is for lower bounds. So we're also going to prove lower bounds on these probabilities. For which we need an initial input lower bound to work with. This is a little bit simpler than the upper bound. We just assume it in one direction, that is the diagonal direction, and then we just assume that you have non-trivial fluctuations on the right scale, both above and below the leading order term with positive probability. So these are the assumptions under which we'll prove the main theorem. So if there are any questions about this, please feel free to ask me.
Okay, can you remember the definition of XRZ?
Right, so XRZ is the best weight from 1, 1 to R minus Z, R plus Z. Okay, so moving on to the main results. The first is a lower bound on the upper tail. So these results don't all use all the assumptions, and it's more precisely written out in the actual manuscript. But here I'm just avoiding all those details and just telling you what the bound is. So we get the lower bound of the right order in terms of the exponent. Notice that again it only holds up till R to the 2/3, like in the earlier combined theorem in exponential LPP. And again, the reason is, so you get one way to think about it is, suppose the vertex weights were actually bounded. Suppose they're, say, uniform 0, 1. Then this XR can be at most 2R, because you're going through 2R number of vertices, get from 1, 1 to R, comma R. So it can be at most 2R. So then once T becomes greater than 2R to the 2/3, this thing would be 0. And you can't have any such lower bound. So you only have this kind of behavior up until R to the 2/3. So that's the lower bound. We also have an upper bound. So this is a little bit more complicated. So for one thing, we get the T power 3/2, but we have to pay this kind of logarithmic cost. It's possible that you could remove this with some more work, but it's not that straightforward. And the second thing is that it only holds up until this T to the R to the zeta level, where zeta is something which depends upon alpha. So this is actually would be true even in the true picture, actually, in that even if you actually had vertices which decay as e power minus t power alpha, so the vertex weights decay at that level, you would expect this kind of thing, basically because after that point, the individual vertex weights play a bigger role in the overall distribution. So in fact, we think that there should be an expression for zeta of alpha, which I'll just mention. I haven't written it out on the slides. That zeta of alpha should be 2 alpha over 9 minus 6 alpha, which if you take alpha equals 1, like in the exponential case, that would be 2 over 9 minus 6, which is 2 over 3, which as we saw is what you get in the exponential case. But modulo these two facts, you get the right exponent of 3/2. Okay, so these were the upper tails. You also have lower tails. Oh, and remember that the lower tail exponent is bigger. It's 3 instead of 3/2. So again, the lower bound is up till order R to the 2/3. You have the right lower bound. Again, R to the 2/3 is because after that point, the probability becomes 0 because the vertices are non-negative. And then you have the matching up in exponent upper bound on the lower tail. And notice that this one, it just holds for the entire tail after a point. That's, again, the same reason. After a point, this probability becomes 0. So the bound is really trivial after that point. Okay. So now I'm going to give you flavors of the proofs for, if possible, all 4 bounds. And if depending on time, we may stop early. But we'll start with the upper tail. And before we start with so I'm going to start with the lower bound and the upper tail. Before we get to that, I'll just tell you a basic overarching theme which holds for both tails. And the basic theme is we look at the geodesic path at smaller scales. But of course, the question is, which scale do you look at? And interestingly, we use the same scale for all the arguments. Now I'm going to tell you the reason that we picked that particular scale to study it at. So let's look at suppose we're looking at the event that the geodesic has a high weight of mu r plus t times r to the 1/3. This is the sort of what we're trying to bound. And what I'm going to say is also applicable if it's minus t instead of plus t. But for concrete, let it be plus t. And now let's look at a 1/k fraction of the geodesic path. So for geometric reasons, you might expect that the weight of this fraction should be proportional to the size of the fraction, in that the blue part's weight should be 1/k of the total weight, which would suggest that its weight should be mu r over k plus t r to the 1/3 divided by k, right? On the other hand, the 1/k should also obey kpz fluctuations. So it should typically have fluctuations on scale r by k to the 1/3. So you would expect its weight from that point of view to be typically mu r over k plus some constant c times r over k to the 1/3. So there's this kind of tension between this uniform spreading of the weight across the geodesic path and the fact that each part has to still obey kpz relations. And we're going to use this tension in the arguments to get this upgraded bounds. But basically, the way to resolve it is to hope that the two things are the same. And if you do that, if you equate the two things, you see that you want, ignoring the constant c, you see that you want r over k to the 1/3 to be approximately t times r to the 1/3 over k. So you equate it, you cancel out r to the 1/3, you bring the k over here to the left-hand side, you get k to the 2/3 is roughly t, so k is roughly t to the 3/2. So this is the scale we're going to look at things. So 1/t to the 3/2 fraction of the geodesic. And the reason is that at that scale, the typical fluctuation agrees with the kind of uniform division of the weight. Okay. So now we can do the upper tail, the easier half, which is the lower bound. So let's look, and this is really going to use superadditivity, which we mentioned earlier, quite heavily. In fact, most arguments do. So let's take these two, fix these 2 points in the picture. K is 3. So r over 3 and 2r over 3. Let's look at the path which goes from 1, 1 to r over 3, and similarly from there to 2r over 3, 2r over 3, and then the last third. So I'm calling the first part xr over k1, xr over k2, xr over k3. So the sum of these 3 things is at most the weight of the geodesic path, right? Because the green path has no constraints to pass through these two given points, and it can therefore have a higher weight. So now suppose you knew that each of these 3 subpaths was at least mu r over k plus c r over k to the 1/3. If you knew this, well, then you would have this lower bound on xr of k times the fluctuation plus mu r. If you just work it out, it's k to the 2/3 r to the 1/3. And remember, we're setting k to be t to the power 3/2 up to constants. So this is exactly mu r plus t r to the 1/3. And so the event that each of these things has typical fluctuations will imply the event that xr is big, on the level we want. And also note that because xr over k uses different parts of the curve or different parts of the environment, they're independent random variables. So it's very easy to estimate the probability that I just mentioned. So now it's just a product because of the independence, and we've assumed that this thing is at least delta, right? That was the lower bound assumption. So this is at least delta to the k. K is t to the 3/2 up to constants, and so this is the lower bound. So if you remember, the lower bound only held up till order r to the 2/3. So you might wonder, where did that play a role over here? And the basic point is that r over k, you're working on the lattice. So r over k cannot become less than 1. And because k is t to the minus 3/2 or t to the 3/2, that means that this has to be at least equal to 1. And that, if you just rearrange it, it becomes the r to the 2/3 bound on t, which is imposed. Okay, so this uses superadditivity and an independence thing to get the lower bound quite easily.
I mean, there's a question, maybe a
Oh.
clarification. So about the colors that you're using, what is the green path, for example?
Oh, I'm sorry. Yeah, the green is always going to be the geodesic or its weight, and blue will always be the smaller scale quantities. Okay, so that was the easier half. The harder half is the upper bound on the upper tail. So this is really what we're calling bootstrapping, because we're going from a very, so remember we're starting with a stretched exponential assumption. So we have a e power minus t to the alpha bound on having a large fluctuation of order t. And we want to upgrade that to be 3/2. That's the basic task at hand. So just for simplicity, let's assume we actually had the opposite bound. So we knew that we knew that xr is less than or equal to some of the smaller things. So remember, this is not true. We actually have we're greater than or equal to, but just because if I assume this less than or equal to bound, then the event that xr is big implies that the sum of xr by k is big. That will make it easier to explain what's going on. But also note that in the real situation, the sum of xr over k is going to have a mean difference from xr. And in fact, the order of that mean difference is k to the 2/3 times r to the 1/3. And you can just see that from the expressions for the expectation we've already assumed. So this is what we're trying to estimate. And the first term is mu r minus er to the 1/3. Each of the things in the sum, excuse me, is mu r over k minus this constant times r over k to the 1/3 multiplied by k. So the mu r's cancel out. What you're left with is k to the 2/3 r to the 1/3. So this is going to put an upper bound on how big we can make k, which will be important soon. Okay, so the point is we're assuming this subadditive assumption, which is not correct, but just for simplicity. So the event that this is big implies the event that the sum is big with the same expectation. These things, the blue things, are independent, but we'd like them to be mean 0 as well to apply some concentration estimates. So we'll replace the expression of xr with the expression of the sum. And to do that, we have to pay the mean difference between the two quantities. So we subtract off this k to the 2/3 r to the 1/3. So obviously we'd like this thing on the right-hand side to be positive. So we can't take k to be too big, but we can take it to be some constant times t to the 3/2 if the constant is small enough so that this whole thing is still of order tr to the 1/3. So that's going to dictate the value of k we take, which notice is still the same as what we said earlier in the theme. So we'll just do that. So you take it to be a small constant times t to the 3/2. And then you can replace this whole thing with half of the same thing. Okay, so this is a sum of independent mean 0 random variables. But notice that the scale on which this fluctuates is not r to the 1/3, but r over k to the 1/3. Right? This is r to the 1/3, so we need to make it of scale r by k to the 1/3. And so for that, we multiply and divide by this k to the 1/3. So now, if you ignore this scaling factor over here, you have a sum of independent mean 0 random variables, all of order 1, essentially, if you take the scale to the left-hand side. And they're also all alpha stretched exponential random variables. They all, by assumption, they all have this alpha decay in the tail. This is good. So this is where we're going to use some concentration estimates. This is quite an intriguing connection, actually, which we'll discuss a little bit more soon. Basically, if the exponent alpha is between 0 and 1, then concentration of measure tells you that the sum's tail decay is similar to the tail decay of a single random variables. So that's the situation we're in. And therefore, this probability of being bigger than tk to the 1/3 is going to be at most tk to the 1/3 to the power of alpha, because that's the behavior of a single random variable, right? And now k is t to the 3 over 2. And so this is t to 3 alpha over 2. Right? So we've obtained an improvement in the exponent by a factor of 3 over 2 because of this fact that the sum's tail decay is similar to that of a single one's when you're deep in the tail. So this is exactly one iteration of what we call the bootstrap. We started with the exponent alpha, and we got this exponent 3 alpha over 2. And we can just iterate this. Now that we have 3 alpha over 2, we can do it again. And it increases, at each stage, and eventually you will pass 1. Definitely be bigger than 1. So, suppose it's 1 plus delta. So it's e power minus c t to the 1 plus delta. Well, that will also imply e to the minus c to the t, because that's a smaller quantity. And the reason I want to have it with 1 is because, remember, the previous thing was only for alpha less than or equal to 1. So we do it up till we get bigger than 1. That implies we have it also with 1. And then we can apply it 1 last time to get 3 over 2. And that gives you t power 3 over 2. Of course, this is not true because we assume the subadditivity assumption. We'll get to that. But in the basic form, this is the bootstrap. You can upgrade the exponent by a factor 3 over 2 with each round. Of course, one question is, why stop there? Why not do it again? Once you got t power 3 over 2, maybe you can do it again and get something even better, which is not can't happen because it's not true. But you might wonder what goes wrong. And that's very interesting, actually. So the thing that goes wrong is that when alpha is bigger than 1, the concentration behavior is different, right? When alpha is less than 1, less than or equal to 1, the event that the sum is big is basically governed by the event that a single one is big. That's why you have the same tail decay for both. But when alpha is bigger than 1, the concentration behavior is that the deviation gets distributed equally among the k variables. And the reason this happens is basically because the function x power alpha is concave for alpha less than or equal to 1, but it becomes convex for alpha bigger than 1. And this change means that the bound you get also changes. So suppose alpha is bigger than 1, let's do the same calculation. Now this tk to the 1/3 is going to be divided among k variables. So each of them is going to have a tk to the 1/3 divided by k to the alpha. And because it has to happen for k of them, you got an extra factor of k over here. Okay, so this is in the case where alpha is bigger than 1. If you simplify this, it becomes t to the alpha times k to the 1 minus 2 alpha over 3. So you can just factor this. 1 by 3 minus 1 is minus 2 over 3 times alpha, and then you have the t power alpha. And remember, k is t to the 3 over 2. And so the alpha factor exactly cancels the t power alpha factor. And you're left with t power 3 over 2. So at least to me, this is somewhat mysterious that this exactly works out. But yeah, it does.
So can you explain the tail bound again? How did you get it?
This one or the previous one?
This one.
Yeah, so I said that we're going to look at the case that this deviation of t to the 1/3 is basically done equally by each of the k variables. So any single one is going to do a deviation of t to the 1/3 divided by k, and then they all have to do it. So you have a power of k extra coming in, which is this factor over here.
I see. Yeah, that makes sense.
Okay, so that tells you why we can get to 3 over 2 and why we can't get past 3 over 2. But remember, this whole thing was with this faulty assumption of subadditivity, which is not true. So in the actual correct derivation, we have to avoid this problem somehow. And what we do, so the reason why you had this relation is because the green path does not have to do the constraint of going through these particular marked blue points. It can go however it wants, and therefore it has a higher weight. But we can find a replacement subadditive relation if we remove a constraint from the blue paths. And what we do is we don't make it start and end at the same points anymore. So we consider the interval to interval weight instead of the point to point weight. So for example, now we can allow these kind of paths, which don't have to go through, they don't have to be contiguous, but the green one does. And therefore they can do better than the green one. So for example, maybe there's some good stuff, there's a good environment over here, there's a good one over here, but you can't reach both if you're made to go through contiguously. But if you're allowed to cheat and change your starting point, you can get both. So this will beat the green path's weight. And this is going to be basically our replacement subadditive relation for the faulty one we had earlier. But it's still not quite done because we don't know which interval the green path will pass through, the geodesic will pass through. Because for example, with the probability we're trying to consider, it can actually have quite large fluctuations and it can totally avoid these blue paths. So we have to deal with that problem. And the way we do that is that we consider a grid of intervals, basically. So we have this entire grid, and we can then look at which intervals the geodesic passes through. And we make the grid wide enough that geodesic will stay inside the grid with a very high probability. The probability of it leaving is going to be at most the upper tail optimal probability, that is t bar 3 over 2. And notice that if you know that it passes through a particular sequence of intervals, we can apply the bootstrapping idea. Namely, we have the subadditive relation, and we have the fact that the constituent things in the sum fluctuate on a smaller scale. And with those two inputs, we can run basically the same argument we had before to get the improved exponent, given that it passes through those particular intervals. But the problem is we don't know which intervals it passes through, right? So basically, you have to handle all possible intervals. And the other thing is that if you specify a weird selection of intervals, like the one I've drawn over here in blue, then the path has to go really zigzag. It has to really go to the right very quickly, and then go all the way to the left, and then to the right again, and so on. And the earlier thing we did, the bootstrap I described to you, was for the geodesic in the RR direction. It did not have any deviation. But over here, because you're making it go through all these really extreme paths, you have to allow much different directions. And because you want to improve, you want to apply this thing for many, many rounds, you have to improve the tail bound you get in all these different directions with each round. So this is a technical complication. So it means that not only do we consider this grid, we also consider different grids which are kind of deviated by the z amount. And we do the same kind of bootstrapping for each of those directions. And that allows you to get a better bound in all the directions, which then allows you to conclude for the direction you care about, which is the RR direction. And finally, if you do a union bound over all possible choices of intervals, and this is where you get that decrease in the exponent from t bar 3 over 2 to t bar 3 over 2 with the log correction factor, which would not be there in reality, but it's a bit hard to do the union bound without getting that. So if there are any questions at this point, please do ask me. This will be the end of the upper tail argument. Okay. So we can go on to the lower tail then. So just to recall, the lower tail has a higher exponent of 3 instead of 3 over 2. Right, and the basic reason is the upper tail, we got it by bootstrapping, it focused on one path. But the lower tail, so the lower tail means the best path's weight is small, which means that all the path's weights are small. So that's a harder thing to happen. It has a lower probability in this sense. So another thing to note is that the bootstrapping argument I told you, the faulty one with the subadditive relation, actually works for the lower tail. Like when you're in the lower tail, the true superadditivity is the right direction that you want. So in fact, starting with the alpha exponent and doing the same thing we did earlier, you can get that the lower tail has at least e power minus t power 3 over 2 for the upper bound. And that's for a single path, remember. So the strategy is going to be, we're going to use that lower tail upper bound of e power minus t power 3 over 2 for a single path. And then we're going to find t power 3 over 2 many paths. And the probability of them all being small is going to be e power minus t power 3 over 2 times the same thing, which is going to be e power minus t cubed. So yes, a single path being small is t power 3 over 2. There are t power 3 over 2 many paths. So in disjoint areas, therefore independent, which is what gives you this bound in kind of a rough sense. So the goal now is therefore to find many disjoint paths which do quite well in their weights, in spite of being disjoint. So this is where we use something called the geodesic watermelon, which is the maximal weight collection of k disjoint paths between 1, 1, and RR. So here is a depiction of what that looks like in a Poissonian LPP simulation. And I want to point out two things. One is that in the bulk of the environment, in the middle over here, the paths are roughly kind of straight. They can move straight because they have some separation from the other paths. But at the corners, they're very close to each other, and they have to remain disjoint while not losing too much weight. And that means they're very scrunched up. They have to expand their separation very quickly in order to reach this middle part where they can be a little bit more relaxed. So this will be relevant for something I'm going to say soon. So there's a recent preprint which we use, which estimates the probability of this thing's weight, of the weight of the geodesic watermelon. So this preprint is with Riddhi Basu, Shirshendu Ganguly, my advisor Alan Hammond, and myself. And what it shows, or one result in it, is that the probability that the geodesic watermelon's weight is small is itself very small, e power minus k squared. So notice that by small, we mean k to the 5/3 times r to the 1/3. So you might think that, well, maybe it should be k over here instead of k to the 5/3. Like if you have one path being small, that's mu r minus c r to the 1/3. If there are k of them, it cannot do worse than k times that, or it cannot do better than k times that. So you might think it should be k over here, but actually the disjointness increases the loss you feel, and you get something smaller.
Can you remind me the notation XRK?
Oh, I'm sorry. Yes, yeah, so XRK is exactly the weight of the best k paths which are disjoint from 1, 1 to RR. So there's a bit of
in the picture you are considering the k paths, right?
Yes. So this is exactly, so here k is 10 or something. They all start at this corner, they all end at this corner, and they're disjoint, and they are the maximal combined collection of paths. Like no other collection of 10 disjoint paths will have a collective weight higher than this one.
Okay.
So it does not mean that any of the individual paths is the maximal weight path. It's only the collective weight we're considering.
Oh, okay.
Yeah, so as a team, they're going out and collecting the most possible weight. They cannot hit each other. What is the best you can do? Yeah. So the weight loss is going to suffer as a function of k, is k to the 5/3 times r to the 1/3. So as a function of r, it's the same as the single path's weight, but as a function of k, the exponent is 5/3. And the way to kind of see this heuristically is that there are k paths, right? Each of them has k subparts on scale r over k. Just like in the previous discussion, we looked at the scale r over k, in which case it has k subparts. And each of those k subparts loses r over k to the power of 1/3 typically. So then you just multiply k paths times k subparts times loss per subpart, and it's k to the 5/3 times r to the 1/3. Now this kind of heuristic I just wrote here is not true for the geodesic, right? Obviously, the geodesic does not suffer as a function of k a typical loss. And the basic reason the heuristic is correct over here but not over there is because here you have to avoid the other paths, and that gives you puts a constraint on you, so they can't move freely the way that the geodesic can move freely. But on the smaller scale of r over k, at that scale they don't feel each other's presence, and on that scale they can move freely, which is why that's the right scale to look at the fluctuations at, and that gives you this right exponent of k to the 5/3 r to the 1/3. Anyway, so the reason I'm saying this in this detail is because this is going to basically give us the lower tail probability, upper bound of the lower tail probability. So again, we're going to set k to be t to the 3/2. And notice that now you have this nice fact that k to the 5/3 is k times k to the 2/3, which is k times t. Which means the probability that the maximum weight, the best weight, is small, well, that implies that each of the k paths in the watermelon have to be similarly small, right? So if you know that the best path does at most mu r minus tr to the 1/3, that means each of the k paths can do at most mu r times t to the 1/3, t times r to the 1/3, which means you can multiply the weight by k. So you have this implication from the definitions. But kt is exactly k to the 5/3 because of what we've chosen k to be. So you get this thing. And this is exactly what has been bounded in this theorem, right? And that gives you e to the minus k squared, which is e to the minus t cubed. So this may seem a bit mysterious. I haven't told you at all about how this theorem is proved, and I'll tell you a bit about that soon. But this is the entire argument for the upper tail given this theorem.
Just to make some, to see if I understand. So this argument of splitting the k watermelon in k and each of the k parts in k subparts only works for k very large, because you have to assume that at the beginning the path they spread at the end point.
Right. So actually, this theorem is only true for k beyond some constant. Yeah, for k smaller, because you always have these constants. For k small, it gets absorbed in the k to the 5/3 up to the constants. But for as an asymptotic or as a thing which is true for all large k, this is the right power.
Also, the result of this holds for fixed value of k. You can take k as a function of r as well.
It holds for k up to a constant times r. So you
Okay.
can take it to be a function of r as long as it's up to a constant times r.
Because you'll be finally taking k as a function of r, I think.
You're taking k to be a function of t, and t could be a function of r. That's right.
Yeah.
But remember that t is at most r to the 2/3, right?
Mm-hmm.
And therefore t per 3/2 is at most some constant times r. And up till that range, the theorem is true.
I see.
Yeah, that's important. That's true. Yeah, to get the full r to the 2/3 thing, you do need you do need to allow k to depend upon r. Okay. So looking at the theorem, it says that the probability that the entire watermelon's weight is small is very small. And the way the theorem is proved is we construct k disjoint paths which have, with high probability, more than this weight. Right, so if you can construct with 1 minus exponential minus k squared probability k disjoint paths which have weight bigger than this, well then the best k paths must also be bigger than that. And that will give you this upper bound. And the way the construction happens is exactly what I said. You divide up, you make these things go through these rectangles of height r over k and width r over k to the 2/3. And you just make them go all the way through. Because the rectangles are disjoint, the paths are disjoint. And you can estimate, and within this rectangle, the weight of any single part is exactly mu r over k minus r over k to the 1/3. And then you, yeah, and then notice that there are k squared of these, right? There's k in each row, and the total length is k to the 1/3. The individual length is k to the minus 2/3. So the total number of cells in each row is k. Each column is k. So they're totally k squared cells over here, and that's actually the same k squared that appears in the exponent. But you see, this is in the kind of in the middle of the environment. After you have the separation, you can make them go straight. But you don't start in the middle, you start at the ends where you're very close to each other. And you have to get from that very close situation to this well-separate situation. And for that part, you can't do something like this. You have to really make sure you avoid each other more delicately. And that's what the other part of the construction does. You have this kind of dyadic expansion across various levels, which maintains disjointness, but gets the separation you need while at the same time not losing too much weight. So the second thing is more delicate. It's the more important part of the construction. But together you get what you said. You get the k disjoint paths, which suffer the appropriate weight, which you can already see that the right weight loss from this part is what I said earlier. And the k squared and the exponent is coming because you're adding up k squared number of independent things over here, basically. So there's one more problem, which I've kind of not mentioned till now, which is that this construction was done under stronger assumptions. The paper I mentioned does not assume the stretched exponential decay of the upper tail or lower tail. It assumes you have the t power 3/2 assumption. But this is where we use bootstrapping. So as I said, for the lower tail, the bootstrapping argument, as mentioned before, actually works and gets you to t power 3/2. And therefore, if you use bootstrapping, you can get from our assumptions to the assumption needed for this theorem, and therefore you get the result of the theorem, and then you get the lower tail bound. So I won't spend too much time on it. This is what this slide is talking about. But the basic point is bootstrapping, along with the correct superadditivity, gives you the required inputs. Okay, so that is the upper bound on the lower tail. And it relied crucially on this construction of k disjoint paths, which achieve collectively a good weight. And once you have that construction, there's a very simple application of the construction. And the basic point is that the lower tail is governed by this different mechanism of all paths being small, rather than a single path being small, as the upper tail was involved in. Okay. So now we have a lower bound on the lower tail. So we have to get a lower bound on the probability that xr is less than or equal to mu r minus t r to the 1/3, right? Notice that, so again, we're going to look at the geodesic path. We're going to see where it goes and use that to analyze this event. Notice that any path which has transversal fluctuation greater than k to the 1/3 times r to the 2/3 is going to suffer a parabolic loss. And the parabolic loss is exactly k to the 1/3 r to the 2/3 squared divided by r, which if you just, it's k to the 2/3 r to the 4/3 divided by r, which is k to the 2/3 r to the 1/3. What this means is that any path which exits this rectangle R of this width is going to suffer a loss of t. Remember, k to the 2/3 is roughly t. So if you want to force this thing to be xr to be less than mu r minus tr to the 1/3, it's enough to do it for paths which remain inside the rectangle R. Because anything which leaves will do it by itself. It'll lose the weight on its own, typically. So we have to really control the weights of things inside the rectangle, of the weight k to the 1/3, r to the 2/3. And if you remember, this is exactly the width of the watermelon as well. So it's the same quantity appearing in both places for similar reasons. So how do we make the weight of this path inside the rectangle R to be small? We do something very similar to earlier. We consider a grid. This time the grid's width is k to the 1/3 r to the 2/3. The cells in the grid have height r over k and width r over k to the 2/3, same as in the construction I showed you. And so that means there are k-squared cells in the grid, right? K in each row, k in each column, just as before. And this again, this k-squared is going to be the same k-squared which appears in the bound. Because k-squared is theta cubed. T cubed, sorry. Okay. So we need to construct an event which causes the best path within the grid to be small. So we consider the event that the best path or the best weight from this blue interval to the entire next row, which is marked in blue, is small. Small in the sense that it's less than mu r over k minus c times r over k to the 1/3. Okay, so if you knew that, and you knew it for if that is true for every interval in the grid. So for each interval, the weight from that interval to the next row is small. Then you would know that xr is less than or equal to k times the maximum of these interval to row weights. And the reason is, so xr is the weight of the geodesic. So it has to pass through exactly k of the intervals, pass through one interval per row, and there are k rows. And therefore its weight is less than the sum of those interval to row weights. Right? It's similar to superadditivity from before. And if you know that each of those interval to rows are small, well, obviously the whole thing also has to be similarly small. So this is less than or equal to k times, so we're just taking this quantity from over here and putting it over here. So less than k times mu r over k minus the fluctuation, which is again the familiar expression now of mu r minus k to the 2/3 r to the 1/3. And again, of course, k is of order t to the 3/2, so this is mu r minus t r to the 1/3, basically. So that means that if the event that all of these k-squared interval to row weights are small implies the event that xr is small. And therefore, if you lower bound the event that all k-squared intervals are small, that lower bounds the probability that xr is small. So this is not something we've assumed. We've assumed that the weight from a point to another given point is small. We have not assumed that the weight from an interval to a line, a row, is small plus probability. But suppose we knew this, right? Suppose we knew that the probability was at least delta of this weight being small. Well, the nice thing about this event is that it's a decreasing event. So a decreasing event means, suppose you have a configuration of the environment, and the configuration is such that an event happens. So in this case, if the configuration is such that the interval to row weight is less than this quantity. Now suppose you take that configuration and you reduce some of the weights in the configuration. So some vertices, you reduce their weight, you reduce their weights in whatever fashion. We don't care how you do it, but you can just reduce them. And decreasing event means that no matter how you do the reduction, the event is still going to happen. So if you started with a configuration where the event was happening and then you made the weights smaller, obviously that will still make sure that the weight is less than this. It can't increase by you decreasing the vertex weights. And so this is a decreasing event. And the nice thing about decreasing events is that you have a good, well, you have an inequality for lower bounding the probability of their intersection occurring. And that's the FKG inequality, which says that the probability that the intersection happens is at least as big as the product of the probabilities. So in this case, we know by assumption that each of them has probability at least delta. We want it to happen for k squared instances. So it's delta times delta times delta, k squared times. So that's a lower bound of delta to the k squared. Right, because otherwise it would be quite hard to understand the probability of this intersection of so many events, except we know that they're decreasing. So they have a correlation inequality, which is the FKG inequality. So ignoring the thing from earlier of the event that you exit the rectangle, you have this lower bound of delta to the k squared. And that, again, k squared, k is t power 3 over 2, so it's minus t cubed. Yeah. So, like I said, we don't have this interval to row lower bound. We need to prove that, but because of maybe lack of time, let me just skip that. Just go to the conclusion of the talk, which is that, surprisingly, the upper and lower tail exponents of 3 by 2 and 3 can be explained under some natural assumptions by studying these weight maximizing paths, either the geodesic or the geodesic watermelon on appropriate scales. And secondly, there is, to me, a somewhat unexpected connection to concentration of measure, which plays an important role for one of the arguments, namely the upper bound on the upper tail. And just somehow the numerology just works out exactly to give you the right exponent. And finally, the techniques, as you can see, they're mainly geometric. They don't rely on any of the exact things for particular distributions, and therefore should be applicable to other contexts, such as, for example, possibly FPP, first passive percolation, with some modifications of the arguments. And yeah, that's it. Thank you for listening.
Thanks, Milind, for the nice talk. So if anyone has questions, you can unmute yourself and ask.
Can I ask something?
Hi.
Hey, hi. So I mean, yeah, it's interesting. So if you look at it from the point of view of the airy line ensemble, which is this system of mutually avoiding locally Brownian curves, then I've often wondered about the deviations you have at one point. What sends the first curve up high above one point? There's a 3/2 stretched exponential decay of that, and I've been able to see for a while the heuristics of why that should happen in terms of the Brownian-Gibbs property, which is a natural resampling that the object has. But then when you send that curve down deep, and there's supposed to be this exponential power of stretched exponential power of 3, you can ask questions about if you push that top curve down, presumably they come up back quickly and go back to equilibrium as you move to the left or to the right. Do your techniques shed any light on that kind of stuff?
So you're asking about getting the lower bound in the airy line ensemble, maybe, or via the Brownian-Gibbs property, or the lower tail via the Brownian-Gibbs property for the airy line ensemble. That's the basic question.
Well, that's a question, but since you're getting that power of 3 by another means, maybe that could shed some light on it. If you ask the question, suppose you condition the airy line ensemble at 0 to be distinctly negative, a value minus x, where x is quite big, then we know that has a probability that the tail is e to the minus x cubed, and you're shedding light, if I understand correctly, on the geometric explanation for that. So a related question is, if you do that, how long does it take as a function of x for the airy line ensemble to bounce back and recover as you move to the left or right at this point? Now, is it x to a certain power, for example, that it takes to bounce back and to come back to a level around 0, or at least, for example, to get back to half the level, to minus x over 2? So do your techniques potentially shed any light?
So I have thought about this a little bit. I don't know if the techniques themselves do it, but with some Brownian understanding, you would say that with some Brownian assumptions, it would tell you that I think it's on scale root x, I believe, that you come back from x below to a more typical level.
Oh, okay. I mean, known for a while that that's what should be, that happen if you do it the other way. If you make it very big, then I would expect root x. I wasn't sure
or did I mix it up? Maybe, let me just think.
I wasn't so sure whether that would happen when you went in the negative direction.
I have to think about it a bit more. I think that's still true, but maybe I mixed it up.
But I suppose one could view things like geometric watermelons as objects that, you know, somehow as you vary the endpoint, some aspect or remnant of the exceptional geometry that must be in place in order to get a very negative value sort of retains a degree of stability as you vary, and that's related to why the value remains depressed for a while. And I don't know if it forges any connections to ideas that you were presenting or not, really.
Right. So, for example, I mean, back to your earlier question, actually, I think it's believed that if you look at, if you constrain if you condition on the weight being small, so less than x over in your notation, then you can ask, well, what is the fluctuation of the geodesic under that conditioning, which is somewhat similar to what you're asking, I guess. So that should be root x, actually. So that's true. So what this thing does, it gets you almost there, actually. What I've told you about so far. You can use the same techniques to understand the lower tail of a constrained path. So we were talking about the lower tail of the unconstrained path. You can use the same techniques to understand the lower tail of the constrained path within a parallelogram of a particular width. Yeah. You can understand how the tail exponent changes as the width increases. And so, for example, if you have a parallelogram of width L part of the 2/3, then the probability of being less than minus theta will be exponential of minus L theta to the 5/2. Okay. And you see that when L becomes theta to the half, this becomes theta cubed. And in that sense, it answers what you said, but in a more precise sense, it doesn't tell you that the conditional fluctuation is of that order. You can, yeah, so I can tell you more about it later, maybe.
Yeah. Thanks.
So just to see if I understand the discussion. So the point is that if you have the Airy-Lannens ensemble and you take the top curve and you assume that this top curve starts from a very somehow assume some very low value. So the question is to ask how long it takes for the curve to go back to the natural position.
Yes, that's right. So you see, it's doing something distinctly awkward because it's pushing a whole structure below it down, so it has to force other curves down below, and you can ask questions about the nature of that movement as well. But yes, I suppose the particular question I asked was indeed what you just said. How quickly does this thing sort of jump back up to the top?
It's a very nice question. So I think that if according to Milind, it's always, if I understand correctly, according to Milind, so if the curve goes up, like somehow is incredibly high, and it's incredibly low, so the time it takes to go back to some natural position is the same. It's always square root of x.
I think that is what Milind said. He can jump in. For my part, I'm fairly confident that that is the correct answer if you go upwards. I find it just a tiny bit surprising. It's what happens when you go downwards, because I would have thought there would be, in some sense, tremendous pressure to jump back up, but it's not something I'm at all confident about, and I don't actually know what the correct answer is. It may be root x.
That's very surprising if it's correct, because if you go up, it's basically you're decorrelating from all of the other, and then if you go down, you're starting to feel the pressure. But if it's square root of x or both.
In all honesty, that would be my own guess that it would be a bit less, but yeah, I don't know. Yeah.
Nice. By the way, I appreciated a lot the simplicity of your argument, Milind. So
Oh, yeah, thank you.
The explanation of how the exponents come out. So it was very clear.
So for the tail exponent for the small interval to large interval,
Yeah.
do you use similar kind of tricks?
Sorry, what kind of tricks?
Like, how did you prove that lower bound?
Oh, okay, maybe I'll just go back. You asked about this one, right?
Yeah.
Yeah, so you have to prove that the best path from this interval to this whole line is small. And the basic thing is you divide up the line into intervals. So again, because there are decreasing events, if you can show the probability of this interval to any of these intervals is small, you can do FKG to get a lower bound. Now, if you're really extreme, then the parabolic curvature tells you that you're typically small anyway. So you don't have to worry about these ones. They're typically going to be small. But if you're over here, then it's more something you have to think about. So if you're going from this interval to this interval, where typically you're going to be big, but you want it to be small, right?
Mm-hmm.
And there, what you basically do is you consider the event, you draw a point over here behind the first interval, and a point over there behind the second interval, and you consider the event that the point-to-point thing is small, right? And you know that probability by assumption, right?
Mm-hmm.
So if you know that the point-to-point is small, it's quite difficult for the interval to be big, right? Because that means if this is big, but the point-to-point from the backed up points is small, that means that this part and this part are really bad. And that is too unlikely to happen. And therefore, you get a lower bound on this being small, basically.
I see.
Yeah. So the basic strategy is back it up a bit, look at backed up points, look at the event that those are small, which you understand by assumption, and then use that to argue that the interval cannot be big.
Mm-hmm. I see.
But yeah, basically, it's really an application of FKG many times. That's what's happening. Once for this thing. In fact, even over here, what I just told you doesn't quite work. If you allow the intervals to be very big, if you allow this to be of order r to the 2/3, so instead you make it epsilon to the r to the 2/3 for a very small epsilon, you can show it for that. Then you do FKG to get from epsilon to 1, and then you do FKG to get from single interval to the entire line. So it's a number of FKGs actually, if they go into the details.